Hello all, welcome to the unit number 2 applications of matrices. Now in this unit we are going to learn some topics. So after learning this unit, student will be able to define the term algebraic multiplicity and geometric multiplicity of a matrix and can find out modal matrix. As well as student can able to define and use Cayley-Hamilton theorem and Sylvester theorem to a suitable problem, and then demonstrate use of rotation, scaling, translation of a matrix form. So first topic is what is diagonalization of a matrix. So for diagonalization of a matrix, we need model matrix as well as square matrix. So definition is, if a square matrix A is of order n is diagonalizable, then there exists matrix P such that P inverse AP is equal to D, where D is diagonal matrix and P is called as modal matrix. Now if we find out this P inverse AP here, P inverse A into P, then this D matrix is nothing but the diagonal matrix. What is diagonal matrix? Only diagonal elements are present, non-diagonal elements are 0. So this non-diagonal element become 0. Now diagonal elements are nothing but the eigenvalues. So suppose if we have eigenvalues are 1, 2, 3, then this will be the answer for P inverse AP matrix, where this P is a modal matrix which is formed by the columns of eigenvector. A is a given matrix. So if we find out P inverse multiplied by A into P, the answer will be diagonal elements are eigenvalues and non-diagonal elements are 0. So this is called as diagonalization. But for diagonalization, if we know algebraic multiplicity and geometric multiplicity, we can find out it easily. So what is algebraic multiplicity? Let A be a n cross n matrix with eigenvalue lambda. The algebraic multiplicity of lambda is the number of times lambda is repeated as a root of the characteristic polynomial. For example, if we have lambda value is equal to 2, 2 and 3. So what is the algebraic multiplicity for lambda is equal to 2? Algebraic multiplicity for lambda is equal to 2 is 2, and algebraic multiplicity for lambda is equal to 3 is 1. Means how many times that eigenvalue is repeated, lambda is repeated, that gives us algebraic multiplicity. So 2 is repeated here for 2 times, so algebraic multiplicity is 2, and 3 is repeated only for 1 time, so algebraic multiplicity is 1. The next is geometric multiplicity. So geometric multiplicity of an eigenvalue is the number of linearly independent eigenvectors associated with it. Means how many number of linearly independent eigenvectors are there, that gives us geometric multiplicity. So here, to find out geometric multiplicity, we have given formula. In note, first point is, let A be a n cross n matrix with eigenvalue lambda, then geometric multiplicity of lambda. Geometric multiplicity of lambda, it is equal to n minus rank of A minus lambda I matrix. Means first, if we have lambda is equal to 2, 2, 2 and 3, then first we substitute lambda is equal to 2 in this matrix and we find out A minus lambda I. Means by substituting lambda is equal to 2, find out that rank, then n is number of total number, so n is equal to number unknowns, n represent unknowns, so unknown variable minus its rank gives us geometric multiplicity. So lambda is equal to 2, first we get one geometric multiplicity. Similarly same thing we will repeat for lambda is equal to 3, again we find out its rank by substituting lambda is equal to 3 and we subtract it from number of unknowns, then we get geometric multiplicity for lambda is equal to 3. So this is the formula for geometric multiplicity. Now if we know algebraic multiplicity and geometric multiplicity, we can tell that whether the matrix is diagonalizable or not. So if algebraic multiplicity, second point is, If algebraic multiplicity of each eigenvalue is equal to geometric multiplicity, then only matrix is diagonalizable. This is very important point. If algebraic multiplicity for lambda is equal to 2, suppose we have lambda is equal to 2 to 3 again, 2 to 3, then algebraic multiplicity for lambda is equal to 2, algebraic multiplicity is equal to geometric multiplicity, then we say that matrix is diagonalizable, otherwise not. Similarly, if all eigenvalues of matrix A are distinct, means if we have lambda value is 1, 2, 3 or minus 2, 3, 4, then if all values are distinct, then matrix is always diagonalizable. At that time, no need to find out its algebraic and geometric multiplicity. Directly you can find out diagonalizable matrix. Next, matrix P is formed by grouping the eigenvectors of A in square matrix form. So we always write P means model matrix. Model matrix is formed by columns of eigenvector of A. Then next, diagonal matrix D is known as spectral matrix and it has eigenvalues of A as its diagonal element. So at this point I have already told you D is diagonal matrix which contain diagonal element as eigenvalues and non-diagonal elements are 0. So that will be the answer for diagonalization of a matrix. So first we see the example. Determine whether the matrix A given as 1 1 3 1 5 1 3 1 1 is diagonalizable. If diagonalizable, find model matrix and diagonal matrix. So first we find out here A minus lambda I matrix. A minus lambda I, it is equal to, subtract lambda from the diagonal element, so it is 1 minus lambda, then 1 3, next is 1 5 minus lambda, then 1 and 3 1 1 minus lambda. So this is A minus lambda I matrix. After that we write its equation, which is lambda cube minus s1 lambda square plus s2 lambda minus determinant of A equal to 0. This is the usual procedure. First find out this, second write down this equation, then find out S1. S1 means sum of diagonal elements. So 1 plus 5 plus 1, it is equal to 7. S2 is sum of minors of diagonal element. Here instead of matrix, this is determinant, not matrix. So did find out sum of minors of diagonal element. So minor of this 1, minor of 1 is 5 1 1 1, neglecting that row and column in which it lies. Similarly, minor of 5 is 1 3 3 1 and minor of 1 is 1 1 1 1 1 5. So here we get S2 value which is equal to 0. Next, find out determinant of A. So determinant of A value we got, which is minus of 36. Therefore characteristic equation become lambda cube as it is minus 7 lambda square plus 36 is equal to 0. So find out directly roots of this equation by calculator also. So you will get roots is minus 2, 3 and 6. So if roots are distinct, means matrix is diagonalizable. So first question is determine whether it is diagonalizable or not. So it is diagonalizable. If diagonalizable, then find model matrix and diagonal matrix. So here we got that it is diagonalizable, means we need to find out model matrix and diagonal matrix. So to find out model matrix, first we find out eigenvector. So eigenvector formula is A minus lambda I multiplied by x is equal to 0. So we have already find out A minus lambda I matrix. So A minus lambda I multiplied by x, it is equal to 0. Now put 1 by 1 eigenvalues. First for lambda is equal to minus 2. Substitute in this equation. You will get 3 equation, that is 3x plus y plus 3z is equal to 0. Then x plus 7y plus z is equal to 0 and 3x plus y plus 3z. So two equations are same. So we have considered only two equation, that is 3x plus y plus 3z is equal to 0 and x plus 7y plus z is equal to 0. Solve these two equations by using Cramer rule. Cramer's rule is x divided by, again this is determinant, x divided by determinant of 1371 equal to minus y by 3311 equal to z divided by 3117. So it is equal to x by minus 20 minus y by 0 is equal to z by 20, and we denote this by t. So what is the value of x? X is equal to minus 20t, y is equal to 0 and z is equal to 20t. So you can take common term here outside and remaining will be your eigenvector. So minus 1 0 1 is the first eigenvector for the value lambda is equal to minus 2. For second eigenvalue lambda is equal to 3, same thing we will do and we will get another eigenvector, that is lambda is equal to x2 is equal to minus 1 1 minus 1 and x3 is equal to 1 to 1. So for different eigenvalues we always get independent eigenvectors. So this is our model matrix, and then finally diagonal matrix is P inverse A into P, which is equal to D, and we can write this D directly. So only here you have to write P inverse also. Try to find out it by calculator. Write down P inverse matrix and directly substitute here. You will get eigenvalues are minus 2, 3 and 6, and remaining non-diagonal elements are 0. So in this way you can write directly diagonal matrix. Then second example is find the matrix P which transforms the matrix A in diagonal form. So first again find out A minus lambda I. A minus lambda I, it is equal to 2 minus lambda, 1, then 2 and 3 minus lambda. Then for 2 cross 2 matrix equation is lambda square minus S1 lambda plus determinant of A equal to 0. So S1 is sum of diagonal element which is 5, determinant is 4. Substituting we will get again two eigenvalues which are different. If it is different means it is diagonalizable. So directly we can find out here model matrix P to find by finding eigenvectors. So A minus lambda I into x is equal to 0 is the equation for eigenvector. Put lambda is equal to first 1 and then lambda is equal to 4. So lambda is equal to 1, we get first eigenvector which is x1 is equal to 1 minus 1. See how we are getting this eigenvector. First equation we get x plus y is equal to 0 and second equation is 2x plus 2y is equal to 0. If we observe it carefully, both are same and it is nothing but x plus y is equal to 0. So we can write it as x is equal to minus y, or we can write it by x divided by minus 1. X divided by minus 1 is equal to y divided by 1. Y divided by 1. So here x divided by minus 1 and y divided by 1, or you can write minus 1, if you multiply it by minus you will get 1 and minus 1 will be the eigenvector. So this is first eigenvector. Similarly for lambda is equal to 4, again you will get only one equation because for 2 cross 2 matrix always we get only one equation. So another eigenvector is 1 and 2. So columns of first column is 1 and minus 1, second column is 1 and 2. You can write any column first, only corresponding eigenvalue you have to write first. So 1 and 2 is related with 4, lambda is equal to 4, and 1 and minus 1 is related with lambda is equal to minus 1. So here this is for 4 and this is for 1. So we have to write first 4 in diagonal matrix and then next 1. So in this way we will get model matrix as well as diagonal matrix if the eigenvalues are different. If eigenvalues are same, then you have to find out its geometric multiplicity and algebraic multiplicity to check its diagonalization. So these are the some examples you can try at home and find out a matrix is diagonalizable or not. If diagonalizable, then find its model matrix and diagonal matrix. Otherwise you can leave there and then directly write down as matrix is not diagonalizable. So solve these questions at home, and if you have any doubt you can ask your queries to me. Thank you.